as an application of motion in a line, let's consider the behavior of a spring. Here, we'll have a spring in a zero gravity environment. That way, the only force comes from the spring itself. We'll hang our spring, we'll attach a mass to the end, then we'll call the equilibrium position 0. Now, we'll raise our mass to a height of 1 and release. So, this mass is going to oscillate between heights -1 and 1. Why does the spring do this? The spring wants to keep the mass at the equilibrium position, so position 0. When we raise it to a height of 1, that's going to generate a force in the spring pushing down to get the mass to go back to 0. It will get back to 0, but only for a moment. Then it's going to wind up below 0, and the force that the spring generates is going to go in the other direction because it wants to bring the mass back to 0. So there'll be a force going up. The mass gets to 0, but now it winds up above 0, and this motion continues. So that's the oscillation. Now, the function we'll use to model this behavior, our position function, is going to be cosine of t. Recall the rules for getting the velocity and acceleration. Velocity is just going to be the derivative of the position function. Acceleration is the derivative of our velocity function. So we take the derivative. Okay, for the position, we're going to get minus sine of t. Derivative of the velocity is going to be minus cosine of t. So you'll note the position and the acceleration are equal up to a sign. So this means whenever we're in a positive position, okay, if acceleration is a stand-in for force, we're pulling down. If the position's negative, then the acceleration is positive, meaning the force is pulling up. Now, let's look at a few points in time. So if we're at t equals 0, okay, we put 0 into each of our functions. We'll have 1, 0, minus 1. And how do we interpret? So the position equal to 1 is going to mean that we're at our maximum height. Velocity equal to 0 means that we're stopped. So this thing is moving up. It's going to start moving down, which means it has to stop to make the switch. Then, acceleration is equal to minus 1, which just means the force is pulling down. If we try t equal to pi over 2, okay, we put it into each of our functions, we get 0 minus 1, 0. So position 0, which means we're at the halfway point, the equilibrium position. Velocity is a minus 1, which means we're moving down. Acceleration 0, which means we're at the equilibrium position. For this brief moment, the spring has our mass where it wants to be, so there's no force. Finally, let's consider time equal to pi. We put that into each of our functions, and then we note we have the opposite situation from t equals 0. I have minus 1, 0, and 1. So position of minus 1 means we're at the bottom of where the motion occurs. Velocity equal to 0 means we're stopped. So as before, when we get to here, we were coming down, we're going to go back up. So we have to stop to change direction of motion. Then finally, I have the acceleration equal to 1. So we could think of this as just a force pulling us up to get back to the equilibrium position.